Just anybody who asks questions, please raise your hands and wait for the microphone, which I hope reaches you in time. Okay, so this lecture on aging, as announced.
Okay, thank you. So I'm going to continue talking about the same subject with respect to Greg's talk. But of course, as you will see, the point of view is going to be necessarily quite different, but let's try to make as much contact as possible. So this is the usual thing. As you know, when you go from a liquid to crystal, you have a first order transition, and if this happens, you jump, and this is this. But in a situation in which you're creating a glassy solid, what you have, and this you must have seen already 300 times in these days, is that you go from a liquid, and then at a certain point, you follow a line in energy, or this could be volume or whatever, that depends where you notice that the quantities depend on the process. So as soon as you notice that some quantity depends on the speed at which I did what I did, necessarily I'm out of equilibrium. And then, let's say, if on the contrary I can see that from one speed of annealing to lower speeds of annealing, I always tend to get the same, then I would say that the envelope would be the equilibrium line. So the idea is I go slower and slower, or with more complicated processes, and I see things that I immediately recognize as out of equilibrium because they depend on the process. There's always the lingering question, and which we will not answer and we will not know in this life probably, that whether if this is done infinitely slowly there is a true divergence there, meaning that there is really some correlation length that has diverged there, or rather that, well, there is something that is still curved, there is no diverging correlation length, and what we are seeing is simply transient out of equilibrium, only that transient we know could be as long as thousands of years. So if we consider the alpha relaxation, which I defined the other day, and I'm going to redefine today, but you could think of this as the viscosity also, you go in the liquid line, and this would be the envelope of all the lines that are obtained with lower and lower annealing speed. And I fall out of equilibrium at different levels depending on the speed. This is corresponding to these two curves. And one of the things one has to also bear in mind is that just as the system hasn't got the time to equilibrate, you don't expect its viscosity to grow to the level it would have in equilibrium. In other words, when you are making a glass, you fall out of equilibrium, and of course what you get is more fluid than it will be at longer times, because it is working its way to an equilibrium situation where things are much more optimized and are happier where they are and they don't want to flow. And the other thing you know, and this is inevitable, but I will stress it again in another way, is that when you are here, because you did a fast annealing or whatever, then things cannot stay put there. They will be evolving. I am going to say this in a different way in a second, but the fact is that wherever you are, unless you are really in equilibrium, then you will be evolving all the time. And this evolution towards equilibrium is what one calls aging. And the question whether there is a divergence or not is the question whether you can age forever, or there is a point always inevitably at every temperature at which there is a time at which you end by equilibrating. So in actual practical life, it often is a question of whether it will take me 10 to the 9 years to equilibrate or infinity. And of course, it's not a very practical question, but and it doesn't really affect, but we are interested in it for reasons more of principle and of ideals than of actual practice. So aging is working your way to equilibrium, and it doesn't enormously matter if you will eventually equilibrate or you will never, provided that the time in which you're aging is long. I go back to the diagram I did the other day. So you have particles. You have something that resembles a solid in the sense that particles vibrate around positions and then they hop and they exchange, but you have a density profile that wants, an average density profile that wants to stay there. And so the particle vibration, if you do an autocorrelation function, the particle, say, fast motion, the density, sorry, fast variations would be the short times. Then for a long expanse of time, you can consider you have an average profile that has some shape, which is amorphous. And then at a longer time, this profile evolves very slowly at a completely different time scale into something else. This would be the analog of the periodic modulations in a crystal. So as you are aging, you're taking your thing here. While you are in equilibrium, the profiles, so these profiles, while you are in equilibrium in a liquid, they evolve, but there isn't a waiting time notion. You are in perfectly good equilibrium when you are in the true supercooled liquid and in equilibrium. You have these slowly evolving profiles, but the time in which they evolve is long, and it depends on the temperature. So at a lower temperature, this is the typical time it takes for these density modulations to go into something else. On the other hand, if I suddenly quench a system, for example, to this temperature, it turns out that this time scale, it doesn't immediately happen. What happens is that the system slowly accommodates from having a shortish time scale where rearrangements are relatively fast, let's say more or less of the order of what they were at the previous temperature, and then slowly, slowly they work their way to being slower and slower. And this is the aging thing. So aging can be seen here as a tendency to make the average density modulations evolve slower and slower. In other words, what you're saying is because, as I said last time, if a density modulation stays forever, this is a legitimate solid, a true, real, in principle solid. When the system is aging, it's going from being rather like a liquid to being more and more like an ideal solid. So the thing to do, and I also did this last time, is, well, you could say, okay, I have particles, but remember that particles can exchange. This average density modulation is some form of order that is there, but it's an order in the density and not in the identity of the particles. And they also rattle around and can hop and exchange, but this doesn't necessarily mean that this density although it could, of course, but it doesn't necessarily mean that these density modulations are evolving. And you could have different profiles, because, of course, if you could have this profile, I continue this picture, cut another piece of the picture and put it here, and of course I don't get the same profile, precisely because you're not periodic. So you could have another arrangement of particles where they vibrate, but around this sort of density profile. And, okay, if the time scale of evolution of this profile and this profile is infinite, then we would be able to call this and this a state, each one of them a state, because all these different configurations are just occasional positions that contribute to this density profile, and all these distinct configurations are configurations that are different moments of the life of this average profile. But this distinction of states and the very definition of state, you only legitimately can make if the time scale is infinite, because otherwise, in finite time, I go from here to here, and then there isn't any clear-cut notion of what is one state or what is the other. And when this is the case, or when it is not, what one does usually is this free energy landscape in one dimension, there's a free energy, and you say that these three states are here, and that these three states are here, and that there is a barrier in the middle, and then when somebody asks you what this axis is, you change subjects. Actually, you also change subjects if they ask you what this thing is. Because what is a free energy of a system that is outside equilibrium? So in general, you don't take too many questions when you draw this diagram. But almost never people ask questions on this diagram, so there isn't much danger. Okay. So let me go through two nucleation arguments just to convince you that neither this nor this can be really a state which lasts forever if they have higher free energy. We already gave this example the other day. I'm going to also give this one. So the first argument was the nucleation argument. If you really have a metastable phase, you can easily calculate how much it costs to nucleate a bubble. The highest price you can calculate taking into account that you pay in the boundary and you gain in the inside. And you inevitably conclude that the barrier to create this, which happens at a critical radius, which is the worst moment, and then you only gain, happens at a finite energy or free energy. And so a metastable state that has a higher free energy than the lowest density, a higher free energy density, cannot live forever. Here it's a good moment to recall Gilles Tarjus's objection that if I am saying this, then why am I talking about glasses? Because the crystal is there. Let us assume that crystals, you could cook up a system where the crystal doesn't exist. In any case, things that have a higher free energy density cannot stay forever. So when you talk about metastable states, you have to bear in mind that they're not stable forever, unless they really have the same free energy density. There's another argument that is less known but more relevant to glasses, which you can calculate when you want to climb a mountain in phase space. And the mountain is very, very high, the Himalayas, but you have many, many paths. Then the time scale for crossing is depressed by the abundance of paths. Because you don't have to think of a path, an activated situation, as something that happens once in a while. What's going on is that you're trying all the time, and for every time you went to 90% of the barrier and failed, there will be many more times where you went to 80% of the barrier and failed, and many less times where you went to 99% of the barrier and failed, and only very once in a while you went 100% and couldn't make it to the other side. This is like how activation works. So it is normal to think that because there are so many trials per successful paths, having many possibilities is a good thing. And this is, you can prove it. And let me tell you a nice exercise to do with.
The mountain supposed to be represented?
It's a bit related to the don't ask thing. It would be representing a situation, for example, where you're trying to nucleate a bubble, as I said before, but at each progressively larger radius of the bubble you're nucleating, you have many options and not only one. So as soon as the number of options you have when your bubble is growing are many-fold, you're gaining more than the mere free energy of each one of those. So you're gaining with the complexity. But normally this is a bit obvious, but it's also a dynamical argument. And in a way, it's something that when you do replica kind of calculation, this comes in automatically. You get a barrier that takes everything into account automatically. You can make it also dynamically in the sense that this multitude of barriers. Let me tell you this little exercise, which is very nice, and you can take a Langevin equation, a normal Langevin equation, where you're calculating an Arrhenius thing, and do it for this spherically symmetric potential of escaping here. So normally you would get the exponential of this height. But when you do it with a perfectly spherical thing, you can go to spherical coordinates. It's not very hard. What you get is that you get an Arrhenius passage with the potential height of the barrier, but corrected with this term, d minus 1 log of r, which is nothing else than the volume of the rim you're trying, the logarithm, sorry, of the volume of the rim you're trying to pass. So the morals of this little exercise is having this multitude of possibilities depressed your barrier potential by a factor that is precisely the entropy of the barrier. So there you see it in a very concrete example. So, to recap, the nucleation argument, now you can do it taking into account this, and now you can say that even if you are not in a situation where your free energy is really of your state extensively higher, so you don't have a free energy density that is higher. If in any case you have an exponential number of options to go, then you don't stay. So a metastable state that is in competition with an exponential number of cousins of the same free energy density will not survive dynamically forever. So these are two reasons why a glass cannot be something that is merely hanging on a metastable state that is living forever. Okay. Oh, no, I think, oh. So in an ideal life, although most of the talks on glasses are given on the ideal glass transition, whether it exists or not, etc., in an ideal world, and I think that Greg's talk and mine are an exception in a way, the real glass is the ones you see everywhere age, meaning that you can think of it in many ways. You're approaching equilibrium, but if you really like to think in terms of metastable state, you should have to think of something where you have a states are nucleating all the time, and there are so many of them and everywhere, and you should see this as a kind of mess of little droplets building up all the time everywhere and at every scale. So this you could see rather like an evolution that is happening very slowly, and it's a bit inevitable. Okay, so it's an out of equilibrium that is different. There is another example of out of equilibrium that is very important, which is, for example, a diamond is actually not a stable state. It's not truly equilibrium, because truly equilibrium is graphite. But during the lifetime of diamond, which is long, and to the extent that nothing of graphite nucleates suddenly, diamond is diamond, and for every practical purpose, you can consider it equilibrium. Because you either go to graphite or you don't, and while you're there, you're okay, while you're still in diamond. Another example is if in a dark room you put oxygen and hydrogen, unless you do something that makes a spark and boom, an explosion, and then water appears, which is the equilibrium situation, while you have the mixture of hydrogen and oxygen, you have a perfectly good equilibrium gas, which lasts until the time, which actually is finite, for which, boom, spontaneously the whole thing decays into water. Glasses are different, and I think that Greg has made this very clear. You don't have this separation, a clear separation between a place where you are happily in equilibrium and somewhere else where you will go, but while you don't go, you can consider that you're in equilibrium. In glasses, you're never in a stationary situation. Things are happening all the time, so you're suffering the effect of time constantly. Okay, and this evolution becomes slower as time passes. Oh my God. So this is a simulation for a Lennard-Jones system of this correlation function. I'm going to define it in a second, but it's just a correlation function of the density, autocorrelation function. This is the time difference, and this is the correlation, and this is an a young sample, and this is an older one, and an older one, and an older one. Meaning that I have a density profile, and the system has, I don't know, 1 million Monte Carlo steps, and it decays like this. At 2 million, it decays, the density profile decays like this. So, meaning that the density profile is becoming stiffer and stiffer as time passes, and the question whether this will last forever or not is the question whether you will equilibrate or not. These are the beautiful curves of Strauch, I think you have to pronounce it. They have been explained already by Greg, but just to repeat, this is quite amazing. You get a block of plastic and you compress it, and this is how it, or you stretch it, and this is how it responds. And if you do it, you can do it from, I don't know, seconds to years, and it responds proportionally slowly to how old it is. And I think that he stopped in 3-4 years, but apparently it can be done for as long as you care to do it. And I don't know. He mentions in the book that there was a sample that was 20 years old, but it was in a cupboard and not at constant temperature. I don't know if there's older, but so that the piece of plastic, you can give it to an experimentalist and he will be able to tell you how old it is, even in years. And this, without nothing being very obviously obvious in the structure or in anything that you can see by the eye, it looks pretty much the same. This is an example of a response. You are doing something to the thing, and the thing responds by stretching or compressing. It's different from the previous example where I'm doing nothing. I'm just looking at the correlation of things that move spontaneously. Okay, so the promised density is the Fourier transform of the density, the spatial Fourier transform, and the promised correlation is simply the correlation between that component of the Fourier transform. I can choose which spatial oscillation I'm looking at and see how it decays in time. I could also, in principle, I don't know if in practice, apply a field that is conjugate to this response. So imagine that if I get my plastic, and I don't know how, I put it in a potential that itself is sinusoidal. So it will force the system to have sinusoidal modulations of density of this kind. So what I'm doing is pushing the system in that direction of all possible directions. So this is the analog of magnetization on one hand. This would be the analog of magnetization, and this would be the analog of the response to a magnetic field. So you could consider the conjugate quantity. This is not particularly nice quantity to look experimentally. Numerically, you can do this. You could subject the system to a sinusoidal potential and just look to what extent you create this sinusoidal modulation. And I'm going to consider, contrary to tradition, I think, the thing as applied between minus infinity to the waiting time. In books in general, what you write is just a spike of field. You give it a kick at the waiting time, but in fact, you can think of this as just being the integral of a lot of kicks constantly given between minus infinity to t waiting. Okay, so now how are these two things related? Correlations are things where you measure things that happen spontaneously. Responses are things where you kick and you look what happens. So now I'm going to try to introduce a relation between these two things. So imagine in just a simple situation, you have a particle moving in this well at a given temperature. The correlations are related to the correlations, for example, of the position. The position is vibrating, oscillating, diffusing because of thermal noise. On the other hand, you could measure a response, consists of kicking this particle in that, giving it an extra kick in that direction, and seeing how this cloud responds. So unfortunately, you cannot see anything here, but what I intended to do is that the cloud drifts in that direction because you kicked. So you see that these two things should be related, because if this thing is rather round, it's very easy for the system to vibrate spontaneously, but it's at the same time very easy for you to kick it effectively or deliberately in that direction. And on the contrary, if the system is very stiff and it both doesn't oscillate very much spontaneously, neither does it respond when you kick it in that direction. So it's already quite intuitive that correlations and responses should be related in some way. And the way, in fact, it's called the fluctuation dissipation theorem, which says that if I wish to calculate this response to a field applied up to t waiting, and I look at the response at time t, which is total time t, I can relate it to these two correlations, which are the corresponding correlation. This is the usual way in which it is written, which is the derivative of this and nothing else. So basically, the response is the correlation, so it's related to the amplitude of the noise or the spontaneous fluctuations times the temperature, which is also reasonable because if you have a flat thing but you haven't got any temperature, the thing will respond a lot but will not vibrate because you don't have any temperature. So this temperature is... So this sounds natural. It can be proved. It's not hard at all. It's amazing that this is a result that came after the theory of relativity and after quantum mechanics. Well, if you don't count Einstein's result, but the full realization that this was a completely general thing, and in fact that the people to which it is normally attributed are much later, which is quite surprising given what a simple thing it is. So if you plot, the fluctuation dissipation theorem says that if you make a plot of this response versus this correlation, the times have gone away, it's a parametric plot, you should get a straight line with gradient minus 1 over t. So this is a statement of the fluctuation dissipation theorem. So, but let me say that the fluctuation dissipation theorem is even more important than what it seems at first sight. It's not just a trick to calculate one thing knowing the other. And to convince yourself, you can do the following exercise, which is not hard. I'm not going to do it here, but it's not hard at all. You take any system of energy E, you take a harmonic oscillator, this is the harmonic oscillator, and you couple them linearly. Ideally, I should have put here a small coupling constant not to disturb too much the system. So I owe you here a small coupling constant. So this is a harmonic oscillator coupled to the system. So what happens if you do this? Well, you see, the harmonic oscillator you can more or less solve if you take into account the energy as this part as a small perturbation. And this thing you can also solve because once you have solved for x, you can think of x as a field acting linearly on rho, which is a variable of the system. So to the linear level, you can give a solution of this, which will correspond to the harmonic oscillator feels the noise of the system through this term. So x, the harmonic oscillator suffers rho, the fluctuations of rho as a noise. So this is pumping energy into this. But on the other hand, the system feels x as a field. Because you see it couples to him, it feels like a field. So, and this will give you another feedback of the system. So when you do this, the exercise I mentioned a second ago, you solve for x, rho appears as a linear field. This is just the equation of motion of x. And then you say that this thing is the bare one, the noise you would have normally, plus the fact that this is not just your old system, but it's your system that has been affected by x. So there is a feedback thing. And how is it affected by x? Just in the linear manner that the response function of E tells you. Because remember that rho is acting on x is acting on this system as if it were a linear field. So when you do this exercise, plug everything in. Actually, to make it rigorous, you should put many of the harmonic oscillators and couple them very, very little, but that doesn't make the exercise more difficult. You get this equation of motion to the linear level of coupling. And now when you look at this equation of motion, what you discover is that this equation of motion exists, and it is a Langevin equation because this is a noise and this is something else, which you could interpret as a friction term. And indeed, it's a good equation for a harmonic oscillator in a thermal bath of temperature T, provided that the rhos of the original naked system satisfy the fluctuation dissipation equation. In other words, the fluctuation dissipation equation for your original system is telling you that this system is able to behave as a good thermal bath of temperature T for the harmonic oscillator to which you coupled it. And it doesn't need to be a harmonic oscillator, it could be anything. So you see that fluctuation dissipation is telling you something about how two systems talk and exchange energy. This one gives energy, pumps energy into your now I'm going to call this a thermometer because it's a system of which I have complete control and tells me something about the bigger system to which I'm coupling it. So the bigger system gives energy to the thermometer through its oscillations, but it picks up energy through its response, and precisely the fluctuation dissipation theorem is what allows you to say that this is going to be, as it should be, a good thermal bath. So the fluctuation dissipation theorem is, if you want, the ultimate symptom of equilibrium, should be, because it's what's telling you what I will measure with a thermometer, and it should guarantee, and notice that it doesn't actually depend on omega, and it doesn't even depend on what the nature of this thing is. So the temperature, it's what also guarantees to you that the temperature you're going to measure is always the same, hopefully, which is what you wanted in the bigger system. Yes? What? Rho K are the, yes, I did, for example, the density modulations of pulsation K. But it could be, for example, if you're doing an experiment on compression of a bar, it could be simply the length of the bar, and you're coupling the length. I'm going to try to do this. If you have a bar of the system, and you couple it to a harmonic oscillator here, so you have the spontaneous, this is a wall that is super hard and everything, and these, how can I, oh, no, well, okay, thank you. So the response is the response of that Greg and I showed of Strick-Straub, where you push on the bar and you measure how much it contracts or it expands. The spontaneous fluctuations are the spontaneous fluctuations of length. This would be the response. And the oscillator here, which could be just a spring and a ball, are getting energy from the fluctuations, but the ball is also disturbing a la Strick the bar. And this exchange between one thing and the other, the fluctuation dissipation theorem guarantees that you will get the right energy for the oscillator, 2 times a half kT. And this would be a better example than the one I gave of the Rho K. Okay. And what I said here between a system and a thermometer is also true between two systems. So they will not exchange any energy on average to the extent that both satisfy the fluctuation dissipation theorem and, of course, at the same temperature. Okay, so this is an experiment which actually we proposed as a mental thing, as a thought experiment some time ago, long ago, with Letizia Cugliandolo and Luca Pelliti, that you could do for a magnetic system. You put a coil and a capacitor, so you have an LC circuit, which is just like a spring and a ball. And this is a magnetic system, this is the thermal bath, and then you measure the potential, and you see how much energy it picks up, and this is a thermometer, and to the extent that this bar satisfies the fluctuation dissipation theorem, this thing should be in equilibrium at the same temperature, and you would measure the average energy you should measure. Funnily enough, this was one of the rare examples, I think, where a Gedanken experiment became an actual experiment that was done by Nat Israelov and Thomas Grijera, but I'm going to come to this in a second. So, okay, now I'm changing gears a little bit. So, you've had already lectures on random first-order theory. I'm going to revisit it in a very short and very quick way, and in a very different way, in a slightly different way. I don't know if you have seen here density functional theory. This is a theory where you have given a density functional of rho. Rho is the rho we had at the very beginning, the average rho, this one, the average profile. So you may write an equation for the average profile. This has a longer history. And this could be an equation. It contains an entropic term. It contains a kind of interaction term. And if you do it for small densities or for small temperatures, which are parameters inside this equation, you get a flat solution, which corresponds to the liquid. Rho is constant. Average rho is constant. But what people discovered is that as you lowered the temperature or increased the average density, you got into a crystalline solution. So the optimum of this free energy was a periodic thing. And then what other people realized later is that, in fact, you not only get that, but you also get solutions that are like chaotic. They are amorphous. They are non-periodic. And these correspond, or you think of them, as the configurations of a supercooled liquid. So this is the situation. You have a temperature, which is a parameter in your equation, and you minimize, and up to here you get only the constant solution, which represents a liquid. Then you jump to a situation where the best thing is a periodic solution, which is a crystal. But then you get to a moment where there are many, many other solutions. This would be free energy. Now it's well defined because it's just the value of the functional. And you would get many, many solutions and coexistence of both of the crystal, the liquid, and the many, many solutions. And you say that the supercooled liquid is represented at the same time by all these states and by the flat solution. And, well, okay, so then don't look too much at this. But the idea is that if I make a cut along the green line, what I would see is a lot of, this is the log of the number of these solutions. At very, very low ones, there are not many. The lowest of the lowest is the crystal. Then I have an exponential increase, so they become more and more numerous until at a certain moment they are no longer at a certain height. What happens exactly here, nobody knows, and it's very important for questions of the actual true glass transition. It is very important to know whether this falls like this or like this, but I'm not going to go into that. And also what happens between crystal and the first amorphous solutions. It's not very clear, and it would be very nice to have it clear, because then we would know if between a crystal and a glass or a supercooled liquid, we have a lot of intermediate things, or no, there is just a gap and nothing in between. This would be very nice to know, but of course we cannot know all these things in so much detail. The solutions to this, mainly by Chandan Das Gupta and collaborators, are what you can do with a computer these days, but you cannot do miracles. And okay, and the liquid solution, I said, that is represented both by this line and by this multitude of solutions, because if you do the Gibbs ensemble and you write as a Gibbs sum of all these solutions, which is a way of refinding equilibrium, your equilibrium happens in the saddle point of this equation, which is exactly where the gradient of this curve, which represents the log of the number of these solutions, is exactly 1 over t. This is in equilibrium. So this is a very crash course on random first-order theory. The story is longer, and I'm going to go through it, but you've already seen it 2 or 3 times. The idea is that what Kirkpatrick, Tirumalai, and Volines realized is that this thing, you could model it rather than having space and all the problem, with a discrete set of variables interacting through a random interaction, which is, for example, cubic. 3-spin. And that this thing is a caricature of this. Since this lends itself, fully connected, so everybody interacts with everybody via a random interaction. So these are the models that are usually called random first order, but this is as well a random first order theory, provided this correlation is calculated self-consistently. So Kirkpatrick, Tirumalai, and Volines had this, what I think is the brilliant intuition that you got but you got essentially the same phenomenology from this and from this, but this gave you some advantages. First of all, that you lost all the community of concrete people, which is because obviously people who could easily swallow this one were not so easily convinced to buy this one. But the advantage was that a lot of theoreticians knew what to do with this. And so in the 90s, there was an explosion of results, including analytical results for the equilibrium situation, including the exact solution of the out-equilibrium dynamics, and including lots of knowledge of the landscape of this energy landscape that are by the form of the landscape, how many states, where they are, how far are they. And essentially what one can say is, and this is what usually is called a random first order scenario, but bear in mind that already Kirkpatrick, Tirumalai, and Volines had realized that this is also the random first order scenario. And if you don't buy the p-spin, which you may be justified in not wanting to buy, this is a bit more palatable. Okay. And, okay, so then this is a mean field theory. Everybody's interacting with everybody, and people are trying to go beyond mean field painfully and for the moment with semi-phenomenological arguments. Okay, so what is relevant for us is that, as I told you, you could solve exactly the dynamics of associated with this thing. And above TC, and this is something that Kirkpatrick, Tirumalai, and Volines realized, and this was for them, I imagine, a revelation, you get exactly the mode coupling equations, which already existed for the supercooled liquid. Whatever you think of the mode coupling equations, it's a little miracle that they appear exactly and naturally as this. Below TC, it turns out that you could also solve it analytically. And what you find is that it's not correct to plug in an equilibrium solution because the system never equilibrates. And it ages very much like in Strick's experiments. And the model does this for you. You don't have any choice here. Here, the model is well defined. You have to solve it. There's nothing to do. And you solve it, and you get aging in the response in the correlation, just as you would get in an experimental system. Just as, I mean qualitatively. And what happens is that, well, you get, as you approach the transition temperature, you get this time scale becoming longer. This is the mode coupling phenomenology, which was well known by that time. And you get response functions, which nobody cared to calculate in mode coupling because it's an equilibrium theory, and both things are related by the fluctuation dissipation theorem. In any case, if you make a plot of C versus chi, you get straight lines at the temperatures at which you are in equilibrium. Now, I told you that below the transition temperature, you could solve exactly the system for the correlation and the response. You didn't assume fluctuation dissipation. There's no reason there should be fluctuation dissipation because this is an equilibrium theorem. So, but you are allowed to do a plot, a parametric plot, the 1 hour curve of correlation against the 1 hour curve of response, the 10-hour curve of correlation against the 10-hour curve of response. And when you did this for the analytic solution, what you find is that, at least for longish times, this curve becomes something like this. All the curves fall into roughly the same. I say roughly because it's an asymptotic statement. It's at long times that they really get on top of one another. And you get, just as a fluctuation dissipation, just respecting the usual one as for this regime, which corresponds to this part of the curve, and which corresponds to the rapid motion. So the rapid motion behaves exactly as you would expect a system in equilibrium. But funnily enough, you get a straight line for the other regime. And because it is a straight line, and by analogy, you may, if you want, call this effective temperature. So this was a discovery on a model on which you could say everything. And what you, on this family of models, what you get, and which is crucial, is that for every observable that you do this, because remember that a correlation can be a correlation of many things, and you only have to choose the appropriate response and put them in correlation one with the other, in relation. For every observable, the length of these segments may change, but you get at equal times that at the same corresponding times, you get the same effective temperature for all observables. So this is something that you expect of a temperature. Yeah? sorry, there's a -1 here, which, and another -1 here, sorry. And a minus. But the T meant associated with, yeah. So this was a surprise, and let me say that there was no understanding as to why this should happen. Okay, so so the natural thing to do later was to go to a real model, simulate it, and see whether you saw something like this. Now we're entering the world of conjecture because there's no way to solve. This is a simulation of a binary Lennard-Jones glass. We cannot even dream of solving this, but we can do an aging simulation and a response simulation. And this is taken from an article of these gentlemen. And what you see is that, for example, for a rho k, where k is the density modulation at this k, you get something like this. They did it for many k. I didn't put it for clarity of presentation, but you get the same kind of broken curve with parallel lines. But I thought it was nicer to put, this is the self-diffusion of this is a binary mixture, so you can do the self-diffusion of a big particle and of the small particles, and you get lines that are very well parallel to this one. So you don't get this straight because this is a long distance thing, so that you don't see in this plot the rapid vibrations. So first of all, a two straight line thing seems not completely out of question. And the lovely thing is that different observables seem very parallel, which there was no way to see this or to imagine this previously. And this was inspired by theory. Okay, so this is a nice thing. We don't know if this is exact or not, or if this becomes exact or not. We just observe that in a realistic system, it works rather well. And go back to this example, which is the reason why we introduced this thought experiment. You can tune this, but now you want to measure which temperature. Well, I want to measure this one, which corresponds to low frequency. So in the paper where we proposed the effective temperatures, there was the proposal to do this, but with the LC circuit tuned to see the low frequencies, because if not, you're mixing up the fast and the slow. And Nat Israelov and Tomás Grigera did this, and, well, I cannot say that they found good evidence for the existence of fluctuation, dissipation being funny at low frequencies and in the same, but you cannot, there isn't yet an experiment on this kind of system where you see a beautiful two straight lines. I mean, these are very difficult experiments to do, but it goes in a good direction. Oh, sorry, I haven't said it. This is a piece of glycerol below the glass transition, this thing. Yeah. Many more sophisticated things have been done, but already this is quite sophisticated because you have to be at very low temperature, you have noise everywhere. These are hard experiments. And the people who have done this, the group of Lyon, the group around Nat Israelov, etc., are people who really are strong, and it's really hard. So, yeah. Let me go to just, yeah, ask me the question.
Yeah. No, can those experiments answer some of these questions?
Well, okay, this is my next transparency. So this naturally begs the question, well, okay, this has a definition which is what it is. It's a very strict definition. It applies exactly for a model. It's not a fit parameter. You're not allowed to do anything with it. But you would say, well, this cannot be entirely independent of the long history of fictive temperatures that I believe starts with Tool in the 30s or 40s, or I don't know. It is not something that has the same, exactly the same origin, but so it seems difficult to avoid putting them together, and one should. But at the same time, you cannot, how can I say this? You cannot impose the things on something that is a definition to a set of phenomenological ideas, because these are things that one can represent the other, but they cannot be identical because there isn't an identity between phenomenology and... So it's for anybody to choose. I mean, the reason why we chose a different name was not to impose anything, but we did cite the papers or some of the papers on that. So I don't know. The relation is somehow there, but it is not something one-to-one because fictive temperatures are something that was brought up phenomenologically with a certain freedom that you have when you do that. So you have to. Yeah. Yeah. So what Silvio is asking is, I could do something the other way around. So I could, on my analytically solvable, unrealistic model, do the construction that you do when you construct a fictive temperature. And the answer is that yes and no. I mean, yes, it is related to the temperature, which when you prolong is the one where they intercepts, but you have to correct for the size of the specific heat correction of the size of the states and that. So it's not identical. So already with the most naive definition, it doesn't give you a fictive temperature. You can arrange that, and maybe in the literature of fictive temperature, there is an idea of arranging this also in the same way. I have no idea. But in principle, if you do it naively, you don't get quite the same. You get something that the effective temperature is of the order of the glass transition temperature, but it's not quite the same. So there again, you have to say exactly what you mean. But I personally believe that deep down there is, of course, that this is creating, at least for these things we can solve, the manifestation of an ideological scenario that is the one of fictive temperatures. Okay. So let me tell you what they are not, because there is something very easy to confuse. The naive thing is to say, but a fictive temperature given, or sorry, an effective temperature, the way this one is defined, is nothing but the hangover the system has from the moment it fell out of equilibrium. Because the effective temperature indeed is roughly of the order of the transition temperature, you could say, well, so this is just modulations of density that happened and remained as I crossed the transition. Let me show you that this is not a correct interpretation. So what happens? Imagine I have a model, like, for example, the kinetically constrained model Rob was describing. So you will have regions that move fast at a given time, and other regions, this is all very schematic, that move slowly. You will have this kind of heterogeneities. You've seen this, you've heard this many times. This is all schematic, so don't take very seriously the shape or anything of the regions. I am in the aging regime. So these regions that move slowly, they are representing the tail of the correlation, the long part. So they are the ones that are at a high effective temperature. And the rapid regions are the ones that are almost in equilibrium. They're responsible for the fast correlations. So they are the ones that are at the low temperature, at the equilibrium temperature. So paradoxically, already you see that this is a bit surprising. The most immobile regions, the ones that move the less, are the ones that, from this point of view, are the hotter. So the question is, could one say that simply when you cross the transition, these heterogeneities got frozen in, and so this is why these regions are at the temperature where the transition occurred? This would be the naive and most natural expectation. The answer is no, because you know that the correlation, we've seen this, is going to zero all the time. Even the slow correlation is going to zero all the time. So this means that these heterogeneous slow regions are moving. They are not always the same with time. So during aging, who is slow and who is fast is renewing again and again given time. And however, you still have that the slow parts are at a higher effective temperature. So whatever makes the effective temperature what they are is something a bit more subtle than that. So paradoxically, it's the slow regions that are responsible for this. And TF is not the result of heterogeneities being frozen in across the transition, for the simple reason that these heterogeneities will renew and displace during aging. given sufficient time. And the reason why the effective temperature then stays of the order of the glass temperature has to be more subtle, because it's not merely a hangover from high temperature. There's something more to it. I could perhaps try to say something about what could this possibly be, but let's not do it. Okay, so now very, very quickly, rejuvenation and aging. So I'm going to describe a situation where I take a model of these and I stir them. So for theoretical purposes, it is better and it is easier to stir things in a spatially random manner. This is not very good for an experiment, but you want to get rid of shear bands and all the paraphernalia of really, I mean, shearing a glassy system, which has all sorts of subtleties. I mean, when I say shearing, I mean shearing extremely strongly. So typically, if you do this with granular matter, you know that you're not going to have an easy. So for theoretical and purely theoretical and even numerical reasons, it's better to shear things like this, you know, in a random, like you would stir things with a fork. If this stirring for a supercooled liquid and even for an out of equilibrium supercooled liquid may shear thin the system into it becoming a fluid. Shear thinning it exists, but not any stirring will shear thin you into becoming a fluid. And Greg said this today, that not any stress is going to rejuvenate you, but definitely you can have supercooled liquids that are out of equilibrium. So they are, in a sense, glasses. And if you stir them randomly, probably with stirrings that are gigantic in an experimental context, you can, well, you definitely fluidize them, and then if you stir them a lot, you can fluidize them a lot. In those cases, you may make the aging stop, and then you really make the system stationary. But it is now stationary, yet out of equilibrium, but for a different reason. It is not out of equilibrium because it is aging, it is out of equilibrium because you're stirring it. So now what you get is that in those situations, you have a correlation that falls, and this becomes shorter when you stir harder, no, because it shear thins. And the response time also becomes shorter when you stir harder. And now you can amuse yourself doing the plot. And if you do the plot, and this is very surprising, or was at least very surprising to us, you get the same plot you would get roughly with the same system while it was aging, but for a different reason. Now it is out of equilibrium for a different reason. It is because you are stirring it. However, the kind of behavior, if the stirring is not monstrously large, is very, very similar. But now you're in a situation where the system is not aging at all. It is stationary. So this is the other phase of aging, if you want. You don't see it in time because you stopped aging, but you see it in this effective temperature done this way. And you can do a plot of drive versus temperature and do, as I did the other day, this would be a 2D version of the Liu-Nagel plot, sort of, with timescales, ISO, as I said the other day, ISO timescales. So the more you are at high drive at high temperature, the more liquefied you are. This is the experimental glass transition, where beyond that the system is too stuck, but this is in a stationary regime. This plot is done on a stationary regime, so this is why I'm allowed to do these lines, because I don't have to talk about history. Yes? Continuous stirring, yeah, stirring, yeah. And this, for the models, we can solve again, and to the extent that we can believe numerical simulations, what seems to be the case is that as you go to slower and slower timescales, there are also lines of ISO effective temperatures. So this point here has the same effective temperature at this point here, but a very different timescale. So this would be a more 2.0 version of the Liu-Nagel plot. Okay, so one last thing is, well, but why, I mean, where does this come from? I want to stress one thing is that when you solve the analytically, what you can solve analytically, you find that this is true, that there is this effective temperature, but you don't really know why. There isn't a simple explanation a priori on the basis of the equations you're solving. So the question is, but why is this happening? So one possibility that has been discussed by a lot of people, I thought Silvio was going to talk about it, but he's probably not. But we already had some in the context of Edwards with Bulbul, is to think that these are all the states in the plot I did previously, if because of aging, instead of being at this point where in equilibrium you would have 1 over T, because of aging or because of stirring, you are visiting the states of this height, then if you assume that these states are sort of populated homogeneously, then you would get that the effective temperature would be related to this landscape. This is closely analogous to supposing that you're hopping between excited states and visiting them flatly. But then again, if this is the case, we have no idea why this would happen flatly. It is a fact that when you solve the equations, you see the effective temperatures, and it is also a fact that when you look at the expectation values, they correspond to what you have here. But why this should happen, we don't really know. At a personal level, I mean, I had read Edwards' paper on these flat measures, and like most people, I think, thought them unreasonable because he was supposing something that there's no reason on earth why it should happen out of equilibrium, that you have some form of equilibrium-like behavior. But then we realized that what you were observing in these mean field models of glasses was exactly doing this for no reason that we could and that we can understand. And okay, this is the situation as it is, but this, in a way, made at least me, for one, look at the Edwards assumption with much more respect, because, I mean, at least a model of glass, which is not very far away from a granular system, was doing this. Okay, the model is schematic, whatever you want, but I didn't put this in. It so happens in the solution. Okay, for reasons that I believe that nobody really understands. So this suggests that, quite amazingly, this flat exploration, or at least approximate flat exploration, the appearance of effective temperatures and so on and so forth, suggests that there might be laws for slow out of equilibrium, laws for themselves, without having to invoke that the timescales will really become infinite. If they're long enough, then there are a number of things you can say. You're out of equilibrium, and still you can say perhaps a number of general things where there is a really strict theory, not yet completed, but there might be behind. And this is a way of thinking that is not what StatMech people like to do, because StatMech people like to calculate partition functions, and this will be of no use here, or not much use here, but it's interesting to think along these lines, because in real life, after all, glasses, even the people who believe more seriously that there is an infinite correlation length, these very same people believe that the actual correlation length in a true glass is 4 or 5 interparticle distances, which is not great. And in a spin glass, which is the case where everybody believes there is a growing correlation length, the best experiment is around, the best ever experiment or simulation is a correlation length of something like 10 or 15. So you see, it's never spectacular. So it would be nice to have laws for things that are, let's say, pre-asymptotic. One, because we don't know, and we're not sure whether ever, as Greg said today, we are going to really get an infinite length. And also because it would be nice to have a theory of what is life, of what life is about. Okay, thank you very much.
Yeah, on the last point, that a lot of people use.
Where is it? Ah.
Yeah, many people use this Edwards-Anderson analogy, and I've been using it myself too. But it's essentially for quenched randomness, right?
Well,
randomness of J
yeah,
is quenched.
No, let me go to this. I didn't mention, I should have, or maybe it is in my list. No, it is not in my list. Okay, what the issue is here, these JIJKs, at least in the first version, there were random numbers. So why? And so this is what you call quench disorder. And a criticism one could make is, well, a glass made of particles doesn't have quench random. But there is an enormous literature at the end of the 90s and the beginning of the 2000s of models that have no quench disorder. They are still mean field, but they have no random quench disorder, and have exactly the same phenomenology. So this really, at the level of mean field, is really no big deal.
Yeah.
In finite dimension, they tend to fail miserably. This is true. But when you take those ones that worked very well and I think Silvio was the first to find this disappointing fact. When you take the very same that worked in mean field and take them down to finite dimension, they fail miserably. We don't understand why, and it may be signaling a weakness of random first order. It may be, yes. But at the level of mean field, you don't have to worry about the fact of these being random.
Since you have mentioned, maybe I can add a couple of words to that. Indeed, what you find with these models, what happens in these models is that although they are disordered, the sample-to-sample fluctuations are very low. But of course, as soon as you go to finite dimension, then you have especially a standard system, and there you have strong spatial fluctuations of the disorder that makes the problem completely different from the mean field case. On the other hand, if you try to solve, and this has been mentioned by Mézard, liquid theory within some self-consistent approximations, so completely non-disordered models, indeed you find back precisely that phenomenology.
Yeah, which is, if you wonder, it is still mean field, but it's a Landau-like theory of glassiness that doesn't need quench disorder. It may be, and this I think goes back to the question, yeah, and it may be that at the end of the day we're going to perhaps discover that models without quench disorder, strictly speaking, don't have a Gaussian transition. It's one of the things we cannot rule out.
Yeah. You said that in the stirred systems also you managed to get a meaningful effective temperature. What kind
which
of
system, sorry?
The stirred
Yeah.
system. Is there a particular kind of stirring? Is it always stirred from the boundaries, or can you put little propellers inside the medium?
No, inside the medium. This is very, very, I agree, unrealistic. But let me give you the stirring example, which is my favorite, and it's the furthest from. If you take a spin glass now, and you make the links asymmetric, so the force A does on B is not quite equal to the force B does on A. This is you can think of this as a stirring. You put a slight something that breaks equilibrium.
Yes. There are currents.
Yeah, exactly.
Yeah.
For spin glasses, it's very clear. This stops aging, and you get the same curves you would get while aging on the time translational invariant thing. This is a case which is easier to get. Then, in a particle system, they did shearing, but the shearing, they meaning the ones who got the curve, Barra and Cobb, but it wasn't random. But of course, in a realistic system, if you applied the kind of shears they applied, which are monstrous, this will be seen on a shear band, and you would certainly not get anything nice. Maybe you could go and look inside the shear band and consider that your experiment. I don't know. So, but what you would do is, I don't know, take two particles and make them interact in a way that wants them to orbit around a little bit, not enormously. Or you could put things inside that do something.
No, the reason I ask this actually is that for internally driven systems, you have a collection of bugs swinging around or something. it's not at all obvious that the fluctuation dissipation ratio should even turn out to be positive, because there are examples of that type of system where you can calculate it and it isn't. So I'm just wondering what restriction there was in this case.
I take the opportunity to say that this kind of plot has been applied for lots of out of equilibrium systems. And of course, the result is that generically you're not going to find anything like these two straight lines. When you're out of equilibrium, you just, what is amazing is that in some cases you do get that, but the surprise is the rule is you get whatever. I mean, sure.
In the case of steady state under CR, how the effective temperature depends on the CR rate?
How does, yes, that's the plot I showed. This, by the way, let me say that this is an artist view we use. It's not, this is not really data. Or what we solved exactly is a model that was solvable. But what you expect is, and this is interesting, you are, even when you are, and this has been checked numerically, even when you are in the liquid phase, so you have a honey-like liquid which is in equilibrium, and now you shear it, what we found is that even in that regime, you see there's this line, so the effective temperature is different from the bath temperature when you shear thin. So even taking an equilibrium system and shear thinning it, not a lot, but shear thinning it somehow, you get this it has already this 2 times scenario, and for the second temperature, the slow relaxations work at a different temperature. And this is okay because this allows me to say that even if there are only supercooled liquids in life and nothing else, even if the glass transition doesn't exist, this is a meaningful thing to do.
I didn't understand what you were saying about the dynamic heterogeneities.
Oh.
So if you, when you measure dynamic heterogeneities at a long time scale, I would think you're seeing regions of fast and slow particles, but can't both those time scales still be much longer than the crossover from the temperature, the time scale where you go from the real temperature to the effective temperature?
No, I mean, in a model that is, for example, to fix ideas in a lattice gas model like the one that Rob was describing, where you have fast and slow regions and you can recognize them and everything, which Rob showed. If you're in the aging regime, these slow regions are sort of growing and then, growing but not growing always in the same direction, and they are sort of, and you know this because when you do the autocorrelation function, it drops to 0, so it means that no slow region stays slow forever. It will be replaced by somebody else, somewhere else. And so you will have to conclude that we know that what is temporarily slow is what is contributing to the slow part of the correlation. But what is temporarily slow now is not the same thing that is temporarily slow later on, much later on, several alpha relaxations later. So then the conclusion must be that this is not merely the same regions that were frozen in from the transition that contribute. You're not happy?
I was confused when you said that the fast regions must be, their dynamics must be on the time scale measured by the actual temperature. Can you imagine a system
this is even a theorem. If you have a system that is out of equilibrium the way you like, and it's in contact with a thermal bath, and if the entropy it is producing is not large, which could be the case of a glass or something that you're shearing not desperately, if the total entropy you're producing is not large, so otherwise the work that you're doing or the fall in energy is not dramatic, then you can prove that all the fast degrees of freedom are at the effective temperature of the bath, which is how it should be, because think of a glass thermometer, a mercury thermometer. It is made of glass. Now this is the most unreasonable thing to do. You encapsule an equilibrium liquid in something that is out of equilibrium, and you stick it to another thing that is out of equilibrium, and you expect this to define a temperature. However, it is okay because both your fast degrees of freedom, the glass and the mercury is one. The three of them coincide. This is a good thing about fast degrees of freedom.
Okay. I mean, in looking at the comparison between what you described and what Greg described, so I think in the experimental studies that he mentioned, well, as long as you had sort of one fictive temperature or fictive parameter to contend with life, the analysis, rationalization of the results was okay. But in the shearing experiments, when you were in principle including a second perturbation, that's when things got complicated. So do you have sort of some way of using the ideas that you described in looking at that situation?
Well, my feeling is that this kind of theoretical line of thought seems to me be pursued to the extent that at each time scale there is essentially one effective temperature. If you have a completely different time scale, then there you can have a third one, a fourth one. Indeed, spin glasses have an infinite amount of them, but separate in time scale. But if you really have many different, you cannot have many different effective temperatures at the same time scale and in this sense make sense of them. So this is one reason why not to call, and this was the main reason why not to try to call this fictive temperature, because you would be telling people not to do what they are already doing. So you know, within this kind of scheme of approximation and of there's once that different observables with only one possible exception, okay, but once that you find many observables and that any two observables have a different one, then you give up the idea. Which is what you do with, as Sriram was asking, a generic out of equilibrium situation where everything does its own thing and there's no reason why anything, and then you give up.
Related to this question, and also going back to this shear diagram, shear diagram that you've shown, the shear stress versus temperature.
Yeah. Shear.
Just before this. Yeah, drive versus drive. This one, yeah. 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 Recently we did a simulation outside TG.
Outside meaning here. Yeah.
And found that it's really self-similar and it collapses into
something.
Into scaling. And from this scaling that we were able to get sort of second interpretation rather than the effective temperature in terms of a second parameter. Notice that the drive would lead to different energy landscape in terms of energy rather than the effective temperature. So
okay,
that's an alternative, at least alternative way of viewing the
I'm not
same thing.
But let me say that if you could rescale this level of drive into, say, zero level of drive, then it means that this point, which is below TG, was scaled to this point here.
No, we scale this way.
But then you scale to an out of equilibrium situation. Because if there's shear thinning, if I take this thing downwards, it depends on the waiting time.
No. We have to discuss.
Okay.
If you apply sufficient stress, you're actually taking the system to a different density.
To a different?
Let's say a different density.
Sure.
Global density.
Sure, but if you are at this temperature, say below TG,
the landscape you have is different, and you can make transitions from.
I agree. Yeah. I agree. So if you were here below TG and you sheared it into some situation that is flowing and stationary, if you are going to map it onto something, you're going to map it onto something liquid, I guess, because if not, what is the waiting time you put? Well, okay, anyway. Let's do this.
I don't know how relevant my question will be, but anyway, I try. I think close to critical point in second order transition phase, there's aging as well, and is there some relation? And can we draw something?
So this is a bit of the kind of question that Sriram was asking. If you the next thing people have done is take other situations where you have some form of something you could call aging. So the most obvious one is domain growth, which is a non-equilibrium situation, and there everything is well understood. And then the third thing that people tried is exactly at a critical point in a ferromagnet, for example. And it turns out that, and if you quench that, it takes an infinite time because you have an infinite correlation length. Well, it's a power law, but then. And it turns out that there you can find, indeed, that you have a well-defined effective temperature for the largest length scales. The reason has to be a bit different from what we're saying here. There's a lot of theory, even people have used very sophisticated things. It's a slightly different situation. It's interesting because you have the longest fluctuations that haven't yet thermalized in a critical ferromagnet, while they haven't thermalized, behave with an effective temperature indeed. And this is away from glass theory. Why people went to look at it because of these, inspired by this situation, but it's not the same line of reasoning. I don't know. I mean, it's an interesting. There's a lot of literature on that, and it's somewhat different.
All right. If there are no more questions, let's thank Jorge again. So yeah, I think the program book says something about poster presentations today, but we basically had 2 poster sessions already. So the second batch is still going to be up till the end of the school, but there's no specific poster session as such today.